We have seen that Lorentz transformation keeps the Minkowski metric unchanged. But what if we ask the reverse question? That is, what are the all possible transformations that will leave the Minkowski metric unchanged? Or more generally, if you are given an arbitrary metric, then how do we find out all possible coordinate transformations that will leave the given metric unchanged? So, let's discuss about it. Welcome to another session of our discussion in physics. This video is a part of a series on the introduction to general theory of relativity. Nevertheless, you can view this video independently as well. In order to answer this general question, we must recap the concept of infinitesimal coordinate transformation. Let us imagine a coordinate transformation where x goes to x prime. For an infinitesimal coordinate transformation, we can express x prime as you see here, where epsilon is a small parameter and xi mu is the 4 vector that generates the given coordinate transformation. We can also compute the corresponding transformation matrix. We have studied earlier that a scalar, a vector or tensor transform under a general coordinate transformation as given here. Now you can ask, how do we quantify the amount of change of a tensor under an infinitesimal coordinate transformation? The answer to this question is usually given in terms of the so-called Lie derivative after the mathematician Sophus Lie. For simplicity, let us start with the definition of Lie derivative for a scalar along the vector field xi mu. I should emphasize a key point here. The difference between the original scalar field and the transformed scalar field is computed at the transform point x prime. For an infinitesimal transformation, we can expand the field to express the Lie derivative in the form that you see here. We can repeat this exercise to define the Lie derivative of a tensor field . As you can see here. Now we can use this formula to compute the change of a metric tensor. Now if the Lie derivative of a metric tensor is 0 along a 4 vector xi mu, then we call it to be a symmetry of the metric tensor. It is also known as the isometry. We know that the covariant derivative of a metric tensor vanishes. The equation then simplifies, and this form of the equation as you see here is known as the Killing equation. It is named after mathematician Wilhelm Killing. The solution to the Killing equations are known as the Killing vectors. Let us now consider an explicit example where we solve the Killing equation to find the corresponding Killing vectors. For simplicity, let us consider the metric of 1 plus 1 dimensional Minkowski spacetime. The corresponding Christoffel symbols are 0, so the covariant derivative reduces to ordinary partial derivative. For different values of mu and nu, we have these 3 Killing equations. These equations can be solved in a straightforward manner as you see here. The solution vectors contain 3 independent constants, namely a, b and d. The different choices of these constants lead to three different types of Killing vectors, as you see here. In 1 plus 1 dimensional Minkowski metric, there are three linearly independent Killing vectors, and these are the generators of time translation, the spatial translation, we may now ask, what is this third Killing vector? In order to identify this, let us recall the usual expression of Lorentz transformation. For infinitesimal Lorentz transformation, we can reduce the expression as you see here. The constructed chi-mu vector is same as the third Killing vector. Clearly, this third Killing vector is the generator of the Lorentz boost. In summary, in 1 plus 1 dimensional Minkowski metric, there are three linearly independent Killing vectors, and these are the generators of time translation, the spatial translation, and the Lorentz boost. If you have any question or comment, please leave them below in the comment section. In case you would like to follow the physics discussion here, please subscribe to this channel.